Hi, so this is welcome to this video, and this is part 10 of our exploration of Lagrange's theorem. And this is part 10 of it, and I mean, so far we've learned what the Lagrange is, what Lagrange's theorem is. We proved that, well, if H is actually a subgroup of G, and the order of and G is finite, then the order of H divides the order of G. That's what Lagrange's theorem says. And so far we've been looking at, well, what are the consequences of this statement? Now, before we realize that if G is actually finite, okay, and from now on when we say G, we're going to mean finite. If we take H, if we take some little g element of big G, then it turns out that the order of little g also divides the order of big G. And this was proved like about 2 videos back, so maybe that's around video 8. And now we're in this other idea. Well, okay, what other consequences are there of Lagrange's theorem? In particular, suppose that the order of G is actually a prime, okay? P is prime. Suppose that the order of G is some prime. What can we conclude? What does that mean? What can we say about G if the order of G is prime, okay? That was the question. So let's think about that. In particular, if order of G is a prime P, well then, can we write G as 1, G sub 1, G sub 2, all the way up till G sub P minus 1? Right? If we can write G in this form, right, then what if we pick some G sub I, some element of G, where G sub I is not the identity, okay? Suppose we did that. We picked some element of G that's not the identity, all right? What is the order of G sub I going to be, is the question, right? What are the possibilities? Given that we know that Lagrange's theorem already tells us that if G is a finite group, then the order of every element must divide the order of the group itself. Given that information, can we conclude that the order of G sub I is either equal to 1 or P? Right. Given that P is prime, well, what possible numbers could divide P? Is it 1 and P? Okay. If order of G sub I equals to 1 or P, well, I mean, could it be both? Could the order of G sub I equal to 1 and the order of G sub I equal to P? What would that mean to say that the order of G sub I equals to 1 and the order of G sub I equals to P? Would that mean that 1 is the smallest power such that G sub I to the 1 equals to 1, and also at the same time P is the smallest power such that G sub I to the P equals to 1? Is that possible? Well, if order of G sub I cannot be both 1 and P, what does that tell us? Does it tell us that order of G sub I has to be one of these, only one of these, and not both of them? Okay. So question, can order of G sub I equal to P? Is that possible? Well, I mean, G sub I the order of G sub I must divide P, and P does divide P, so could it be possible? Is there any reason why? Maybe the question is this way. Is there any reason why we can exclude order of G sub I from being P? Right? Could you think of such a reason? Well, we think of such a reason. Let's think about, how about, can order of G sub I equal to 1? Is there any reason why we would exclude order of G sub I being equal to 1? Okay. Suppose that order of G sub I equals to 1. What does that mean? Does it mean that G sub I to the 1 equals to 1? But if G sub I to the 1 equals to 1, doesn't that mean that G sub I equals to 1? Okay. But didn't we assume that G sub I is not equal to 1? Right? So if g sub I, can g sub I equal to 1 and g sub I not equal to 1? Does that make any sense? Right. So what are we saying here? Are we saying that the order of g sub I cannot equal to 1? Not possible? Okay. If the order of g sub I can only equal to 1 or p, and we've already established that the order of g sub I cannot equal to 1, what does that tell us the order of g sub I must be? Okay. So can we conclude that the order of g sub I equals to p? Alright. Alright, so if the order of g sub I equals to p, what does that tell us about the group G? Right. So if the order of g sub I equals to p, in particular, remember our set G was just 1 p was it p? Alright. Anyways, why are we even writing down the set G for the time being? Okay, well, because it's why we're rewriting it. Didn't we already establish before that G was this? Okay. G was just 1, G1, G sub 2 up to G sub p minus 1. But now we've established that there is some element G sub I in G whose order is p. Okay? Well, if the order of some element of the group G is p, what can we conclude is the question. And what does this tell us? Well, can we conclude at least the following? Let's call this H. Let's call this set H. Let's look at the set H which equals to G sub I to the 0, G sub I to the 1, G sub I to the 2, all the way up till G sub I to the p minus 1. Let's think about this set. Alright? How many elements does it have? Is order of H equal to p? Okay, H is the set. If order of H equals to p, or actually that's a question, is order of H equals to p? Right? How can we determine whether order of H actually equals to p? Right? Okay, maybe ask this question instead. Can order of H be greater than p? Right? We have 0, 1, 2, all the way to p minus 1. Can this set suddenly become bigger than p? Okay. If that's not possible, if order of H can't be bigger than p, we ask another question. Can order of H be less than p? Is that possible? Right. What would it mean for order of H to be less than p? Would it mean that there exists some, let's say, k and m integers such that g sub I to the k equals to g sub I to the m? Here, of course, we're assuming that k does not equal to m. Right? That is, would saying that order of H is less than p be the same as saying that there are at least two elements in H, at least two elements in H that are actually the same element? That is, there is some k not equal to m for which g sub I to the k equals to g sub I to the m. Okay, well, if k does not equal to m, is there anything stopping us from assuming that k is less than m? Okay. What if k is less than m? What would we do with that information? Alright? Well, I mean, g sub I is an element of G. Is g sub I to the k also an element of G? Right. Given that G is closed, can we conclude the following? If g sub I to the k is actually an element of G, does it mean that g sub I to the k inverse exists? If G is a group, and given that G is a group in a group, well, one of the qualities that every element has an inverse. If G sub I to the k is an element of G, can we then conclude that G sub I to the k inverse exists? Okay. Well, now is G sub I to the k inverse the same as G sub I to the minus k? Alright. If this is true, if G sub I to the k inverse is the same as G sub I to the minus k, well, what can we do with our equation here where we assume that G sub I to the k equals to G sub I to the m? Right. If k does not equal to m and G sub I to the k equals to G sub I to the m, well, then what are we saying? And obviously, let's recall that these k and m were powers of G sub I in the set H. So that means that in addition to k being less than m, we also have that they're at most p minus 1 and at the very least 0. Right? K and m are, the lowest they can be is 0 and the largest they can be is p minus 1, because their power is being picked from g sub I to the g sub I to some power. Okay, well, supposing that two elements in H are actually the same, for some k and m, one of these powers 0, 1, 2 up to p minus 1, suppose we have that g sub I to the k actually equals to g sub I to the m. Okay, well, if we multiply both sides by the inverse of g sub I to the k, what would we get? Would we get g sub I to the minus k times g sub I to the k equals to g sub I to the minus k times g sub I to the m? Okay. If this is true, aren't we saying that 1, what's g sub I to the minus k times g sub I to the k? Is it 1? So are we saying that 1 equals to g sub I to the m minus k? Okay. So question, if m, we said before that k is less than m is less than or equal to p minus 1, and the lowest this k or m can be is 0. Okay, well, actually the lowest k can be is 0. Okay, what does that tell us about m minus k? If m and k are between 0 and p minus 1, is m minus k also less than or equal to p minus 1? And of course less than or equal to 0 is the question. Right? If this is true, if k and m being between 0 and p minus 1 also implies that m minus k is between 0 and p minus 1, well, what is this statement telling us? What does it mean to say that g sub I to the m minus k equals to 1? Isn't that the same as telling us that there exists some natural number L, there exists some L natural number such that L is less than P minus 1, is less than or equal to P minus 1, which wouldn't that be the same as saying that then L is less than P? So are we saying that there exists some natural number L, namely m minus k, such that L is less than P and g to the L equals to 1? But if g to the L equals to 1, right, so here the natural numbers are being taken to start from 0. But if g to the L equals to 1, how can, maybe let's put it this way, is it possible, does it make sense to get some L less than P and have the g sub I to the L actually equals to 1? Is this possible given that we know that the order of g sub I equals to P? What does it mean for the order of g sub I equal to P? Does it mean that P is the smallest natural number such that g sub I to the P equals to 1? If P is the smallest natural number such that g sub I to the P equals to 1, how can some L smaller than P be such that g sub I to the L equals to 1? Okay, so what are we saying here? Are we saying that if k does not equal to m, that is, if we look at our set H, if none of these powers from 0 all the way to p minus 1, if none of these powers, if we picked any two powers that were different from each other, then the elements g sub I raised to those powers will not be the same. Is that what we're saying? Are we saying that if k does not equal to m, then g sub I to the k can never equal to g sub I to the m? Right? If that is true, what are we saying really? Are we saying that every element in this set H, g sub I to the 0, g sub I to the 1, g sub I to the 2, up to g sub I to the p minus 1 are distinct? If all the elements in H are distinct, what can we conclude? Can the order of H ever be less than P? Right. If the order of H can't be less than P and the order of H can't be greater than P, what does that tell us? Can we conclude that the order of H is P? Alright. Okay, so if we've concluded, right, so here's what we have now. Okay, we got a set H, wrote it as 1, G sub I to the 0, G sub I to the 1, all the way up till G sub I to the P minus 1. Okay, we're saying, well, if order of H equals to P, right, what do we know order of G is? Order of G also equals to P. What is that telling us? Order of H equals to order of G, right? And the other thing we're asking, well, if we looked at the set G, the set H, is every element of H also in G? What are the elements of G, of H, of, in what form? Question is, we now know that order of H equals to order of G. Does that mean that H equals to G? Is that true? Okay. What would we need to show in order to conclude that H equals to G, given that you already know that the order of H equals to G, order of G? Would we need to prove that H is actually a subgroup of G? Suppose we knew that H is a subgroup of G and order of H equals to order of G. Would that be enough for us to conclude that H equals to G? Right? Right. So let's think about whether H is actually a subgroup of G, a subset of G or not. Well, so let's ask the question, is H a subgroup of G? Right? What are the elements of H? Well, all elements of H are of the form G sub I to the L, right, or to the R, let's say, where R is some number, right, between 0 and P minus 1. Oh, this was G to the 1, G to the 2, G to the 1 to the 0, right? G sub I to the 0, right? Well, what is G sub I to the R really? Is G sub I to the R the same as G sub I times G sub I times G sub I times G sub I multiplied R times? If that's what G sub I to the R is, and every element of H is of the form G sub I to the R, right? And we took G sub I, remember, to be an element of G. If G sub I is an element of G, and G sub I to the R is just G sub I multiplied by itself R times, can we conclude that G sub I to the R is also an element of G? I mean, if G is closed, right? That's another thing about groups. Groups are closed. If G is closed, can we conclude that, and G sub I is an element of G, can we conclude that G sub I to the R is also going to be in G? Okay. If we can conclude that, then if we've shown that for every element G sub I to the R in H, G sub I to the R is also in G, can we conclude from that that H is actually a subgroup of G, subset, sorry, of G? All right. So if H is a subset of G and H, order of H equals to order of G, isn't that the same as saying that H equals to G? Right. So if H equals to G, right, and remember H was written like this, if H equals to the G and we've written, that means that G equals to H equals to G sub I to the 0, G sub I to the 1, G sub I to the 2, all the way up till G sub I to the P minus 1, alright? Suppose this is actually our group G. I mean, if this is our group G, what does this tell us? Is this telling us that G can be generated by only one element? Right? That is, if we know G sub I and we know the order of G, we know we can generate all the elements. One element is G sub I to the 0, G sub I to the 1, G sub I to the 2, G sub I to the P minus 1, right? g sub I to the p minus 1. So really, well, any group that can be generated by one element is called cyclic. Right? Cyclic coming from cycle. Why do you think the name cycle is appropriate? Let's think about it. We start from 0, right? G sub I to the 0 is the identity. Then G sub I to the 1 gives us some other element. G sub I to the 2 gives us a different element. G sub I to the p minus 1 gives us a different element. And what does G sub I to the p give us? Given that the order of G sub I is p, well, that just gives us 1, doesn't it? Alright? So, I mean, let's see if the cyclic part makes sense. But first is, let's first be straight here. So, can we make the following conclusion now, that if the order of G is some prime p, then G can be generated by any non-identity element of G. Right? And what does it mean to be able to be generated by just one element? Right? So being generated by one element means, right, that, well, I mean, you can write it in this form: G sub I to the 0, G sub I to the 1, G sub I to the 2, up to G sub I to some power, and then we stop. Right? Or every element is of the form G to some power. Right? That's what we mean to be generated by only one element. And in particular, we're saying this group is called cyclic. Why does the name cyclic make sense? Alright, so let's think about that. Well, let's use our example of group H here. So let's say we started from 0, then we went to 1. Let's say p was 5, the prime was 5. Right, so G sub I to the 0 would give us the identity, right? G sub I to the 1 would give us, well, just G sub I. What would G sub I squared give us? What about G sub I cubed? And let's say G sub I to the 4, and let's go to G sub I to the 5. Okay, so that's our setup so far. Right, so we start from let's write a little better. So that was not a hard eraser, but all right, cool. Let's call this G sub I to the 4. Let's call this, let's erase some stuff. Let's call this G sub I to the 5, and we're going to call this G sub I to the, no, actually, oh, geez. We're probably making this more complex than it should be. Let's see, G sub I to the 4, 3. We'll call this G sub I to the 4, and then we'll call this G sub I to the 5. Alright, so let's think about that. Well, G sub I to the 0 will just give us, well, whatever G sub I to the 0 is. In this case, it's the identity, isn't it? Then G sub I to the 1, well, will give us some different element. G sub I to the 2 would give us some different element. G sub I to the 3 would give us a different element. G sub I to the 4 would give us a different element. G sub I to the 5 will give us a different element. What about G sub I to the 6? Right. What are we doing here? This is so messed up. Okay. let's write it better. Suppose p is 5. That is our prime. P is 5. Okay. Then let's start from the first element. So would have G sub I to the 0, right, give us the identity. G sub I to the 1, G sub I to the 2, G sub I to the 3, G sub I to the 4, right? And then, so basically what we're getting here is, we start from G sub I, we go to the 0, we go to G sub I to the 1. From G sub I to the 1, we go to G sub I to the 2. From G sub I to the 2, we go to G sub I to the 3. From G sub I to the 3, we go to G sub I to the 4. Question, what about G sub I to the 5? What's that going to be? Well, if the order of G sub I is 5, p which equals to 5, what do you think g sub I to the 5 is? Is it going to give us the identity? If g sub I to the 5 gives us the identity, well, isn't the identity also the same as g sub I to the 0? Okay, so what's that telling us? That g sub I to the 6 takes us back to g sub I to the 0. Okay, what about g sub I to the 7? Well, g sub I to the 7, can't we write that as g sub I to the 6 times g sub I? Sorry, that's a super I, not sub. Can't we write g sub I to the 7 as g sub I to the 6 times g sub I to the 1? Now, if g sub I to the 6, we said that was the identity, so isn't this the same as just g sub I? So are we saying that g sub I to the 7 just takes us all the way here? What about g sub I to the 8? Will g sub I to the 8 be equal to g sub I squared? What about g sub I to the 9? Will g sub I to the 9 just give us g sub I cubed? What about g sub I to the 10? Will that just give us g sub I to the 4? And so on and so forth. So, and then, does it make sense why we call the group cyclic? If the entire group can be generated by just one element, like g sub I, does it make sense why the group is cyclic? It has a cyclical nature to it. See if the name makes sense to you. And our main conclusion here is, this is the conclusion we've been able to draw. See if you can now put together all the pieces. That if order of G is some prime, if order of G equals to some prime P, then G is cyclic. In fact, if the group is cyclic, a natural question to ask is, well, what are the generators of the group G? Right? And this is the in fact part. In fact, every G sub I in G such that G sub I does not equal to 1 is a generator of G. And we can write the group G as just the generator of G sub I. See if this statement, you're now able to prove this statement. If a group has prime order, then the group is cyclic, and in fact every non-identity element is a generator of the group. Alright, we actually finished before time this time. Thank you very much for watching this video, and please think about what other consequences are there of Lagrange's theorem. We hope it's becoming clear that Lagrange's theorem is very deep and has a lot of consequences. What else can we conclude from Lagrange's theorem? Because, I mean, in case there's confusion, well, at what point did we use Lagrange's theorem in establishing our proof here? Right? And we're claiming that this theorem that we've just done is a consequence of Lagrange's theorem. Can you recall why it is a consequence of Lagrange's theorem? And in particular, what other consequences are there? What other consequences of Lagrange exist? Can you find them? Right. Thank you once again for watching this video, and have a relentless week. Bye.